Hello everybody, in this lecture we will be solving 1994 IMO problem number 4. Here is a view of this problem. We need to find out all the ordered pairs m, n of positive integers such that this expression turns out to become an integer. Let's assume that mn is such a pair that makes this a positive an integer, I should say. Then in that case, I will just apply the division algorithm. Namely, I will just divide this integer, now that I know it's an integer, by n and see what we get here. So we have n cubed plus 1 over mn minus 1 is equal to, upon division by n, let's say that the quotient is q, and we also have a remainder of r. Here q should be greater than or equal to 0 and r should be strictly less than n. Less than n. And now here if I do the cross multiplication and expand it, so this would imply that n cubed plus 1 is simply equal to qn plus r times mn minus 1. Further expanding on this one, we have q times mn squared, so this one, and then minus qn plus rmn minus qn, and finally minus r. Now I can take both sides in mod n. So if I take it in mod n, I would get 1 is congruent to, so this n cube would vanish, n square vanish, this is vanishing, so we have 1 is equal to minus r in mod n, or simply this would imply that r is congruent to minus 1 in mod n. So as a result, knowing also the fact that r is between 0 and n, this would imply r is equal to exactly n minus 1. Now I can plug this back into the equation, namely this one, and so this would make, so therefore we have, let me do it in 2 steps, n cubed plus 1 is equal to q times m times n squared plus r, we replaced it with n minus 1 times m times n minus q times n minus n plus 1. The plus ones would cancel out, and then we can further simplify by n. This would finally imply that n squared after simplification by n is equal to q times m times n remaining, the square is gone, plus the n is gone again, so we have n minus 1 times m, and finally we have minus q here, and then a minus 1 here. Now at this step, before I go further, try substituting n with different values and coming up with pairs that solves this, I would like to take the time to make the following observation. So let's assume again that mn is an ordered pair which makes this fraction a positive integer. Then I claim that if this works, then I claim nm also works. When I say works, make that fraction a positive integer, and it is very clear how that would so we would get m cubed times n cubed plus 1 over mn minus 1. Now we already know this is an integer, that's an integer, a positive integer, so luckily I should be able to split this into 2 fractions, namely n cubed minus 1 over mn minus 1 plus m cubed plus 1 divided by mn minus 1. Now we all when you look at this one, we can easily see that you can factorize this difference of cubes here, and it will cancel with the denominator, so therefore this guy is an integer as well, finally implying that this one is also an integer. So this one being an integer therefore tells us that nm is also an ordered pair, which will also make this fraction a positive integer. So therefore I can without loss of generality make the following assumption, that m is greater than or equal to n for the rest of the discussion, and each time I would just also take consider the symmetry between m and n, and consider the pairs in symmetrical in symmetry. Okay, so let's start with n is equal to 1 in our equation. So if I plug in n is equal to 1, I would get that 1 square is equal to q times m times 1 plus m times 1 minus 1 minus q minus 1. So this would imply that 2 is equal to q times obviously this disappears, so m minus 1, and that's it. So that would further imply that q, which is the quotient in our division algorithm, it is an integer obviously. Q is equal to 2 over m minus 1. So from here we realize that m can only take the values, that's a minus 1 here, m can only take the values 2 or 3, and in both cases we have the different value for n. So therefore we have solutions mn 2 1 is a solution, as well as 3 1, and as well as the symmetry, we need to consider the symmetry 1 3 are also solutions. So far we have found 4 solutions. Now in the next step we can consider for the rest of this discussion, we can just focus our attention on m and n greater than or equal to 2, and then going back to the original formula, namely this one again. So let's continue working on this one. Here I will do the following trick. I will replace the m's here with n. Because n is less than m, it will make the right hand side smaller compared to the left hand side. So therefore I would get that n squared would be greater than or equal to q times n squared, and replace m with n, so something smaller, plus n times n minus 1 minus q minus 1. And after reorganizing this, let's do it, we should get things simplifying. Yeah, so we have n squared on the right side and n squared on the left side, so we have minus n minus q minus 1. I can move things around. Let's take out the so 0 greater than or equal to, so factor out the q. We have n squared minus 1, and then here we have minus n minus 1. So therefore further factoring out the n minus 1, n minus 1 here, minus plus, I think, yeah. So that would give us 0 is greater than or equal to q times n minus 1 minus 1 times n plus 1, but n is a positive integer, so as a result, so this is already positive, suggests that this guy has to be positive as well. So therefore finally so negative, I should say, sorry for that, negative. So that would give us that q times n minus 1 minus 1 is less than or equal to 0, so is less than or equal to 1. And from here this implies that because q and n are integers, this implies the only way this would work is if q is equal to 0 or 1, and in both cases, let's start with the easier case. If q is equal to 1, then it implies that so this case here would imply that n has to be equal to 2, and and then as a result m also comes out as 2 as well. So this is another pair, namely 2 2 works, and I don't have to worry about the symmetry here. So now finally we have this case here. So what happens if q is actually 0 and n is greater than or equal to 2? Then in that case our equation, namely this one, becomes because the q terms vanishes here, so we would get n squared equals m times n minus 1 minus 1. So we would get n squared equals m times n minus 1 minus 1, m times n minus 1 minus 1, the q terms cancelled out, and further yeah, so I can play with this, I guess, a little bit more. I can or let's just directly divide everything by, yeah, let me first subtract minus 1 from both sides. So this would imply n squared minus 1 is equal to m times n minus 1 minus 2. And now dividing both sides by n minus 1, on the left hand side I would be left with n plus 1 is equal to m minus 2 over n minus 1. And I can further move things around. So this would imply that let's move it one more time. So m is equal to n plus 1 plus 2 over n minus 1, but m is an integer, suggesting that n from here it comes out as either 2 or 3, and so if n is equal to 2 here, so 2 over 1 is 2, 2 plus 1 plus 2 is 5, so m comes out as 5. If n is equal to 3, so 2 over 3 minus 1 is 2. So we have a 1 here, 1 plus 1 plus 3. Again, m is equal to 5. So therefore, we would get the pairs 2, 5. Sorry, I should say 5, 2. The pairs mn come 5, 2. But then because I need to consider the symmetry as well, 2, 5 is also acceptable. And also 5, 3. And 3, 5 is also another acceptable solution. So therefore, we looked into every single case, starting with n equals 1, then n greater than or equal to 2, and then looking into subcases, different subcases. We are able to find 4 solutions here, 1 more here, and then 4 more here. In total, we have found 9 solutions to this problem. Hope you enjoyed the video, and looking forward to see you guys in our next lecture.